Hello, everyone. Tonight we will embark on a journey into the mysterious depths of the galaxies. Enjoy listening. Galaxies are the universe's way of organizing itself slowly, quietly, and with a kind of effortless elegance that makes human urgency feel a little unnecessary. A galaxy is not just a photograph-worthy swirl of stars. It is a gravitationally bound ecosystem, stars of many ages, gas in multiple temperatures, dust that both hides and reveals, magnetic fields, cosmic rays, and a vast, invisible structure of dark matter that acts like an unseen shoreline holding everything in place. A soft definition: what a galaxy really is. When astronomers say galaxy, they mean a self-contained island of matter held together by gravity. That island can be shaped like a thin disk with spiral arms, or like a smooth ellipse, or like a messy, irregular patch. But whatever its shape, a galaxy is a balance between forces. Gravity pulling inward, motion and rotation resisting collapse, gas cooling and condensing, starlight and explosions pushing outward, time doing what time always does, turning small changes into big history. A galaxy contains visible parts and invisible parts. The visible parts are easier to imagine: billions of stars, glowing gas clouds, and dust lanes that cut across starlight like shadows in fog. But the invisible part, dark matter, often contains most of the mass. If you could see the dark matter halo around a galaxy, it would look like a vast, faint sphere extending far beyond the bright starlight, like a giant, transparent dome that the galaxy sits inside. And galaxies are not isolated ornaments. They live in neighborhoods. Some are in small groups. Some are in huge clusters. They stream along filaments of the cosmic web like lanterns hung on enormous threads. Their lives are shaped not only by their own internal processes, but by the environment around them, the gravity of neighbors, the flow of gas from intergalactic space, and the long-term influence of cosmic expansion. To understand how galaxies form, it helps to begin with a calm but powerful idea. Before a galaxy can shine, it must first have a place to gather. That place is a gravitational well, and the earliest, strongest wells were built mostly by dark matter. Before starlight, the universe prepares the map. In the earliest times, the universe was hotter and denser than it is now. It expanded and cooled. And as it cooled, it transitioned from a bright, ionized plasma into a neutral gas, mostly hydrogen and helium, after a period called recombination. When atoms formed, light could finally travel freely, leaving behind a cosmic microwave background, a faint afterglow that still fills the universe today. If you look at that background carefully, you find tiny variations in temperature and density, small ripples, like a very gentle texture in what would otherwise be smooth. Those ripples matter because they represent slightly denser regions and slightly less dense regions. Gravity amplifies those differences over time. Gravity doesn't need drama. It doesn't need speed. It only needs a difference, however small, and enough time. Dark matter plays a special role here. Dark matter does not interact with light in the usual way. It doesn't absorb or emit photons. That means it can start clumping and forming structure without being held back by radiation pressure, the way ordinary matter once was. Dark matter begins to gather into halos dense, gravitationally bound clumps earlier and more efficiently than ordinary gas can. These halos are the first true containers of future galaxies. As the universe ages, halos grow by merging with other halos and by pulling in more dark matter from the surrounding region. This growth is hierarchical. Small structures form first, then merge into larger ones. It's a slow construction project across cosmic time. Now, ordinary matter, the gas feels the gravity of those halos. It begins to fall inward, but gas behaves differently than dark matter. Gas can collide, heat up, cool down, radiate energy away, form pressure, and develop complex flows. Dark matter is more like a collisionless swarm. Gas is more like a fluid. So galaxy formation becomes, at its heart, a story about gas learning how to settle inside invisible wells. A well forms. Gas falls in. Gas heats. Gas cools. Gas condenses. Stars ignite. Stars push back. The galaxy grows anyway. That back and forth, the push and pull, is the galaxy's long, quiet heartbeat. The cosmic web where galaxies prefer to live. On the largest scales, matter in the universe organizes into a pattern called the cosmic web. Imagine vast filaments, long, thin bridges of matter, stretching across tens to hundreds of millions of light years. Where filaments intersect, matter piles up into dense nodes, and those nodes become homes to galaxy groups and clusters. Between filaments are voids, enormous regions with far less matter and far fewer galaxies. This pattern emerges naturally when gravity amplifies tiny early fluctuations. Over time, matter flows from less dense regions toward more dense regions. The flow is not random. It's guided by the geometry of the gravitational landscape. In this landscape, galaxies are not just placed. They are grown where the flows converge. If you like a restful image, picture a night ocean with slow currents. Over long time, floating material drifts into the same eddies and gathers into islands. The islands don't decide where to be. They form where the current quietly insists. Galaxies form where the universe gathers its resources. Gas falling in, heating, cooling, and the first settling. When gas falls into a dark matter halo, it accelerates. As it compresses, it heats. This is not heat like a campfire. It's thermal energy from gravitational infall. In many halos, especially larger ones, gas can be shock heated to very high temperatures, forming a hot, diffuse atmosphere around the halo. Hot gas does not easily form stars. For stars to form, gas must become cold and dense in localized regions. That means the gas must cool. Cooling is one of the most important and most quietly complicated parts of galaxy formation. Gas cools by emitting radiation. In the early universe, when heavy elements were rare, cooling mechanisms were limited. Hydrogen and helium can cool in certain ways, but efficient cooling to low temperatures often relies on molecules, especially molecular hydrogen, and later on, heavier elements, and dust. As galaxies evolve and stars produce heavy elements, cooling becomes easier. Carbon, oxygen, and other metals provide many pathways for gas to radiate energy away. Dust grains help too, both by radiating in infrared and by providing surfaces where molecules can form. So, galaxy formation becomes easier after the first generations of stars enrich the gas. The universe learns chemistry, and chemistry helps gravity. As gas cools, it sinks deeper. It can begin to settle into a rotating configuration. Why rotating? Because the gas has angular momentum. In a universe with structure and flows, almost nothing collapses perfectly straight inward. Small, sideways motions add up. As the gas contracts, conservation of angular momentum makes rotation more important. The way an ice skater spins faster when pulling their arms inward. A rotating, cooling gas cloud tends to flatten into a disk. This is how many disk galaxies begin. A thin, rotating layer of gas and stars embedded in a much larger, dark matter halo. But even here, the story is never perfectly neat. Gas can come in from different directions. Mergers can disrupt the disk. Feedback can blow holes in it. The disk can reform. The galaxy can wobble and breathe. Still, the disk remains one of nature's favorite solutions. Rotation plus cooling equals a flattened structure. The first stars, when the dark becomes visible. Before the first stars, the universe had no visible galaxies, only matter, mostly dark, drifting and clumping in invisible ways. The first stars, often called population 3 stars, formed from nearly pristine hydrogen and helium. Because the gas had almost no metals, it cooled less efficiently, and that likely led to stars that were, on average, more massive than typical stars formed today. Massive stars live fast. They burn bright. They die quickly, often in powerful supernova explosions. Those early supernovae were transformative. They produced heavy elements. They seeded surrounding gas with metals. They created shock waves that stirred and compressed the interstellar medium. They began the long process of enrichment that would eventually make rocky planets possible. And they began galaxy feedback, the process by which stars, once formed, reshaped the conditions for the next generation of stars. A galaxy is never just a passive container of stars. It is an active environment where starlight and stellar death continuously change the gas. Feedback. The galaxy learns to regulate itself. Star formation is not a one-way street. Once stars form, they influence the gas around them. Massive stars emit intense ultraviolet radiation. That radiation ionizes surrounding hydrogen, creating glowing H2 regions and heating gas to around 10,000 degrees. Hot gas expands and pushes outward. Massive stars also drive stellar winds, streams of particles moving at hundreds or thousands of kilometers per second. These winds carve bubbles in surrounding gas. Then supernovae occur, injecting enormous energy into the interstellar medium. Supernova shock waves can compress nearby clouds, triggering star formation, while also dispersing other clouds, suppressing star formation. Feedback is both creative and destructive. In smaller galaxies with weaker gravity, feedback can be especially dramatic. Supernova-driven winds can expel significant amounts of gas, slowing or even temporarily stopping star formation. In larger galaxies, gravity holds on more tightly, and feedback tends to stir and regulate rather than completely evacuate. This is one reason galaxy formation is not simply gas in equals stars out. The efficiency is limited. Many galaxies convert only a small fraction of their available gas into stars at any given time. And that inefficiency is not a failure. It's the reason galaxies can keep shining for billions of years rather than burning through their fuel too quickly. The universe is economical. It spreads its light over time. The quiet chemistry of enrichment. How galaxies become complex. As generations of stars live and die, they enrich their galaxy with heavy elements. Low and intermediate mass stars gently shed material during late stages, returning carbon and nitrogen and dust to the interstellar medium. Massive stars, through supernovae, return oxygen, silicon, iron, and many other elements. Neutron star mergers, rare but important, produce many of the heaviest elements like gold and platinum, adding another layer of chemical richness. Over time, the galaxy's gas changes composition. It becomes more metal-rich. Dust becomes more abundant. Cooling becomes more effective. Molecular clouds form more readily. Star formation becomes more structured and more efficient in localized ways. So galaxies evolve not only in shape and mass, but in chemistry. Their later generations of stars are born from material that has already lived a stellar life before. That idea is soothing if you let it be. Galaxies are systems where matter is reused, refined, and cycled. Nothing is wasted. Even the end of a star becomes the beginning of something else. Why galaxies have different shapes. When we classify galaxies, we often talk about spirals, ellipticals, and irregulars. Those labels are convenient, but the deeper truth is that galaxy shape is a record of physics and history. Disk galaxies, spirals, and lenticulars are usually rotation-supported. The stars and gas mostly orbit in an organized plane. Disks are strongly tied to ongoing or past gas accretion and sustained star formation. Elliptical galaxies are more pressure-supported. Their stars move in a more random range of directions, like a swarm rather than a coordinated disk. Many ellipticals form through mergers, which scramble stellar orbits and can consume or heat gas, reducing future star formation. Irregular galaxies are often small, gas-rich, and shaped by interactions or internal turbulence. Some are irregular simply because they have not had enough mass or time to settle into a stable disk, or because feedback and environment keep disturbing them. But these categories blur. A galaxy can transition. A disk can be disrupted and later regrown if gas accretion continues. An irregular can become more ordered. A spiral can become quenched and fade into a smoother, lens-like lenticular galaxy. A galaxy is not locked into its first identity. It is always negotiating with its circumstances. Spiral arms, not fixed structures, but patterns. Spiral arms look like they might be permanent physical arms, like the blades of a pinwheel. But in many cases, spiral arms are better thought of as patterns regions of higher density, moving through the disk like a wave. As gas enters a spiral arm region, it compresses. Compression encourages molecular cloud formation and star formation. Young, bright, blue stars light up the arm, along with glowing nebulae. As those stars age and drift, the arm's glow changes. So the arms are often highlighted by youth, short-lived, massive stars that act like glitter thrown onto a moving pattern. This is why spiral galaxies can look so alive. Their arms are places where the galaxy is currently making light. Bars, quiet engines in the middle. Many disk galaxies have bar structures, elongated concentrations of stars stretching across the center. Bars are not just cosmetic. They can redistribute angular momentum and channel gas inward. That inward flow can trigger central star formation, build pseudobulges, and sometimes feed the central black hole. If spiral arms are the galaxy's bright neighborhoods, a bar is more like infrastructure, a slow conveyor belt moving material where it can change the galaxy's future. Bars can form and dissolve over time. They are part of the galaxy's internal evolution, a reminder that galaxies are dynamic even without external collisions. Bulges and halos. The older populations. Many galaxies have central bulges, dense regions of older stars. Some bulges are classical, likely formed through early rapid collapse or mergers. Others are pseudobulges built gradually through disk processes, like bar-driven inflows. Beyond the bright disk lies the halo, a vast region containing old stars, globular clusters, and dark matter. Stellar halos often include faint streams, remnants of smaller galaxies that were tidally disrupted and absorbed. These streams are like fossil footprints. They tell you that galaxies grow by eating and being eaten, by merging and mixing. And because halo stars are often old and metal poor, they preserve information about early epochs. Galaxies keep memory in their outskirts. Galaxy mergers, slow collisions in a sparse universe. Galaxy mergers sound violent, and in some ways, they are gravitationally, but they are not like collisions of solid objects. Space is mostly empty. Stars are far apart. When two galaxies pass through each other, direct star-star collisions are extremely unlikely. The drama happens through gravity. As galaxies approach, tidal forces pull out long streams of stars and gas. Disks warp, orbits change. Gas clouds collide and compress, often triggering bursts of star formation. Starbursts, where the galaxy briefly forms stars at an unusually high rate. If the galaxies have significant gas, mergers can drive gas toward the center, fueling intense star formation and potentially feeding the central black holes. When black holes accrete rapidly, they can become active and influence the surrounding gas through radiation and jets. Eventually, the two galaxies settle into a new equilibrium. If it was a major merger between similarly sized galaxies, the outcome is often more elliptical in shape, with randomized stellar motions. Mergers are a key path for galaxy growth. They are part of the hierarchical building of structure in the universe. Small things merge into bigger things. And because they take hundreds of millions to billions of years, they are cosmic slow motion. Quiet growth, feeding from intergalactic space. Not all growth comes from mergers. Galaxies also grow by accreting gas from their surroundings. Gas flows along the cosmic web, sometimes shock-heated, sometimes streaming in more directly depending on the halo mass and cosmic era. Once gas reaches the galaxy, it can settle into the disk, replenish star-forming material, and maintain star formation over long timescales. In the early universe, accretion rates were higher. Galaxies were building quickly. Later, accretion often slows, but it can still matter. A galaxy that continues to receive fresh gas can keep forming stars. A galaxy that is cut off from fresh supply may slowly fade as it uses up or heats its remaining gas. So, part of a galaxy's fate is about supply lines, whether it stays connected to the streams of the cosmic web. The central black hole, quiet most of the time, powerful when active. Most large galaxies appear to host a supermassive black hole at their center, with masses from millions to billions of solar masses. A black hole itself emits no light, but the material around it can. When gas falls inward, it forms an accretion disk. Friction and magnetic effects heat the gas enormously, and it can radiate across the electromagnetic spectrum. In this active phase, the galaxy's center can outshine the combined light of the entire galaxy. This is an active galactic nucleus. The most extreme are quasars, visible across immense distances. What matters for galaxy evolution is feedback. Powerful radiation and jets can heat surrounding gas and drive outflows, potentially reducing the cold gas available for star formation. This may help explain why many massive galaxies are quenched, why they stop forming stars, and become dominated by older populations. But again, it's not constant. Many supermassive black holes are quiet for long periods. Activity can come in episodes, turning on and off as gas supply changes. It's less like a monster constantly feeding and more like a deep engine that sometimes finds fuel. Quenching why some galaxies stop forming stars. Many galaxies, especially massive ellipticals, form few new stars today. Their light is dominated by older, redder stars. They are sometimes described as red and dead, though they are still full of motion, structure, and history. Star formation can slow or stop when cold gas becomes unavailable or unable to collapse into dense clouds. Several processes can contribute. Supernova feedback can expel or heat gas, especially in smaller galaxies. Black hole feedback can heat gas in massive halos or drive it out of the central regions. Environmental processes can strip gas. In galaxy clusters, the intracluster medium can remove gas through ram pressure stripping. Tidal interactions can also disturb or remove gas. Gas supply can decline. If a galaxy stops accreting fresh gas, it may gradually use up or stabilize what it has. In some galaxies, gas remains but is too warm or too stable to fragment. The galaxy becomes quiet, not because matter vanished, but because the conditions for collapse no longer happen easily. A quenched galaxy is like a city after construction ends. The buildings remain, the lights still glow, but there are fewer new structures going up, galaxy clusters, and the intracluster medium. Galaxies often live in groups and clusters bound by gravity. Clusters can contain hundreds or thousands of galaxies, embedded in a deep gravitational well dominated by dark matter. Between the galaxies lies the intracluster medium, a thin gas heated to tens of millions of degrees, emitting X-rays. This gas can have more mass than the galaxy's stars combined. It is part of the cluster's baryonic content, and it plays a role in how galaxies evolve inside the cluster. As galaxies move through this hot medium, their own gas can be stripped away. This can shut down star formation and transform spiral galaxies into gas-poor systems over time. Clusters also encourage gravitational encounters, not always direct mergers because speeds can be high, but frequent interactions can harass galaxies, disturbing their disks and changing their morphologies. Environment can be destiny. Not always, but often enough to shape galaxy populations across cosmic time. Rotation curves. How we discovered dark matter's grip. One of the cleanest lines of evidence for dark matter comes from galaxy rotation curves. If you measure how fast stars and gas orbit at different distances from the center, you might expect the speed to drop in the outer regions, like planets in the solar system orbit more slowly when farther from the Sun. But in many galaxies, the orbital speed stays roughly flat, far out into the disk. That implies there is extra mass beyond what we can see mass distributed in a halo. This unseen mass makes galaxies stable. It changes how they respond to interactions. It affects how they form and how they hold together. In this sense, dark matter is not just a missing piece. It is the frame the visible galaxy is mounted on. The multicolored galaxy, seeing in many wavelengths. When you look at a galaxy in visible light, you mostly see starlight and some glowing gas. But galaxies are multi-wavelength objects. In ultraviolet, you see young, hot stars and recent star formation. In infrared, you see dust warmed by starlight. Dust can reveal star formation hidden behind opaque clouds. In radio, you can map cold hydrogen gas, the raw fuel for future stars, and molecular gas traced by molecules, like carbon monoxide. In X-rays, you see very hot gas in galactic halos, supernova remnants, and energetic regions around black holes. No single picture is the galaxy. Each wavelength shows a different layer of the same system. This is a quiet truth about astronomy. The universe is not one scene. It is many overlapping scenes, and our eyes are only one kind of detector. The early universe, when galaxies were more chaotic. If you observe very distant galaxies, you see them as they were billions of years ago. In those early times, galaxies were often smaller, more gas-rich, and more irregular. Star formation rates were higher, mergers were more common, many galaxies looked clumpy and turbulent. That makes sense. The universe was younger and denser. Gas was flowing in quickly. Structures were assembling rapidly. Feedback was intense. Over time, many galaxies settled. Disks became more common and more stable in some mass ranges. Others merged into larger spheroids. The overall cosmic star formation rate peaked several billion years after the Big Bang and has declined since as gas supplies changed and galaxies matured. Cosmic history has a rhythm, a youthful era of rapid building and bright activity, followed by a longer era of slower growth and quieter light. The Milky Way, our home as a case study in calm motion. The Milky Way is a barred spiral galaxy with a disk, spiral arms, a central bulge, a halo, and a dark matter envelope extending far beyond its visible edge. The Sun orbits the center at a distance of roughly 26,000 light-years, completing one orbit in a little over 200 million years. That means the Sun has gone around the galaxy only a few dozen times since it formed. The galaxy's timescales are so long that even the solar system feels like a short chapter. The Milky Way contains star-forming regions in its disk, especially along spiral arms. It has dust lanes that block visible light and make the galactic plane look mottled and textured. It has globular clusters orbiting in the halo. It has streams of stars from past mergers. It has satellite galaxies like the Magellanic Clouds, interacting and exchanging material. And at its center is Sagittarius A*, a supermassive black hole that is mostly quiet today, with occasional flares. The Milky Way is not finished. It is still growing. It is still accreting. It is still evolving. End quote. Andromeda and the future. A slow meeting. Andromeda, the nearest large spiral galaxy, is moving toward the Milky Way. Over billions of years, they are expected to merge. The night sky will change on timescales that are far beyond human generations, but still part of the galaxy's life. The merger will be a gravitational dance, not a catastrophic star collision event. Stars will mostly pass by. Gas may compress, triggering star formation. The final result may be a larger, more elliptical galaxy. Even our cosmic neighborhood is still under construction. A gentle summary of the whole process without rushing. A galaxy begins with a gravitational well, often formed first by dark matter clumping in the early universe. Gas falls in. It heats, then cools. As it cools, it settles, often into a rotating disk. Dense regions collapse into stars. Those stars light the galaxy and enrich it with heavy elements. Feedback from stars and black holes regulates gas, sometimes triggering star formation, sometimes suppressing it. The galaxy grows by accreting gas from intergalactic space and by merging with other galaxies. Its structure changes. Disks form and reform, bulges build. Halos accumulate remnants of past mergers. In some environments, gas is stripped or heated, and star formation slows. In others, fresh gas keeps arriving, and star formation continues. Over billions of years, the galaxy becomes not just a collection of stars, but a record of everything that happened to it. A galaxy is gravity plus time, given enough material to work with, a final image to drift into sleep with. Imagine the universe before starlight, a dark, expanding space filled with thin gas and invisible dark matter, with only tiny ripples in density. Those ripples deepen. Dark matter gathers into halos, silent and steady. Gas drifts inward, warms, cools, and begins to settle. Rotation flattens it into a disk. In the densest pockets, the first stars ignite small points of light that turn the darkness into a place with landmarks. More stars form. Supernovae bloom and fade. Heavy elements spread like a slow perfume through space. Dust grains form. Clouds become richer. Cooling becomes easier. The galaxy brightens, then steadies, then changes again. Spiral arms appear as patterns in motion. Nebulae glow softly where new stars are born. Older stars drift into quieter orbits. A central black hole waits in the deep center, mostly silent. Far outside, the dark matter halo holds the galaxy together like an unseen embrace. And all of it continues patient, gradual, unhurried while you rest. Galaxies are the universe practicing patience with infinite consistency, gathering, cooling, turning gas into stars, turning stars into elements, and turning time into structure. Sweet dreams.